All right, people. So we're moving on here to section 4.4, the properties of logarithms. Now, actually, a lot of these we have already seen. In fact, these first four we have already met in the previous talk. But just to remind ourselves, let's talk about them again. That for any base b that's relevant here, greater than 0 or not equal to 1, and not equal to 1, log base b of 1 will be 0, since b to the 0 equals to 1. And log base b of b will equal to 1, since b to the 1 equals to b. Okay, and then the next two properties, as we discussed before, and we will discuss even further at length in section 4.5, that log base b of b to the x is just x, and that b to the log base b of x is just x. These two properties together tell us that the exponential function b to the x and the logarithmic function log base b of x are inverse functions of one another. Okay, now these next three properties, though, are ones that we have not yet met. So these are pretty useful for us in terms of simplifying or expanding. Sometimes what's called expanded might be viewed as simplified. I don't know. But they go as follows. That log base b of x plus log base b of y equals to log base b of x times y. So that the sum of two logarithms can be simplified to just one logarithm of the product of the numbers that whose logarithms were taken in the sum. And similarly, log base b of x minus log base b of y will be just log base b of now x divided by y. So that differences of logs turn into logs of fractions. Okay, and then last but not least here is that log base b of some expression x to the p, where p is some exponent, can be simplified as p times log base b of x. This one you can see kind of follows from the first one, since x to the p is x times x times x times x, right? Up p times, let's say. And then p times log of base b of x is log base b of x plus log base b of x plus log base b of x, etc., p times. So it seems sensible that maybe 7 might have something a little bit to do with number 5. So let's see it in action, and then maybe we can discuss about why these three are true. So they first ask us here to simplify these guys to a single logarithm. So they give us log base 5 of 2 plus log base 5 of 7. Well, by rule 5, this one will simplify to log base 5 of just 2 times 7, which we could write as log base 5 of 14. And the next one, they give us log base 3 of 40 minus log base 3 of 5. And by rule number 6, this one should simplify to log base 3 of 40 divided by 5, or rather log base 3 of 8. Okay, the next one's a little bit more abstract and lengthy, but we'll go for it. They give us 3 log base b of p plus 6 log base b of q minus 7 log base b of r. So I'm going to first use rule 7 here and simplify each one of the logarithms by yanking the exponent back upstairs. So we get log base b of p cubed plus log base b of q to the 6th minus log base b of r to the 7th. And now I see here a sum of two logarithms, so I'm going to use rule 5 to simplify this pair and make them into just one. So I'll have log base b of now p cubed times q to the 6th minus still log base b of r to the 7th. And so to clean it up here, I'll invoke rule number 6 because I see a difference of two logarithms. That can be now the logarithm of the fraction. So this becomes log base b of p cubed times q to the 6th divided by r to the 7th. All right. One more kind of along these same lines. They give us now natural log. So we'll say natural log each time. So they give us 12 natural log of g minus 5 natural log of h minus 3 natural log of m. Okay, and so I'm going to do a little bit of manipulation with this before I really simplify it. The first thing that we can do is bring the exponents back upstairs. So we have natural log of g to the 12th minus natural log of h to the fifth minus natural log of m cubed. And notice how I have two things being subtracted. So what I can really do is subtract their sum in total, but in parentheses here. So we have really natural log of g to the 12th minus the quantity natural log of h to the fifth plus natural log of m cubed. Okay. Now in here, I have a sum, so I can turn that into a single logarithm. So my next step will say that I have natural log of g to the 12th minus natural log of the product h to the fifth times m cubed. And now I'll invoke rule number 6 and take the difference here and turn it into the logarithm of the fraction. So the final answer is natural log of g to the 12th divided by the product h to the fifth times m cubed. Okay, the next example asks us to go backwards. And in some instance of your mathematical life, you might actually like to go backwards and have more logarithms, but each with simpler things inside of them. So in this guy, they give us log base 7 of 4 times c times d. Well, we could break this up into pieces. Maybe the first one could be log base 7 of 4 times c plus log base 7 of d, and then further break up the logarithm into now the sum of 3. So we have log base 7 of 4 plus log base 7 of c plus log base 7 of d. So having threefold product inside your logarithm, it just gives you a threefold sum outside. Okay, the next one they ask us for log base 3 of 9p squared divided by q to the fifth. So I'll first invoke rule 6 and give us that we have log base 3 of 9p squared minus log base 3 of q to the fifth. And then I'll further break up the first one because I see it's a product inside there, so I can write that it's log base 3 of 9 plus log base 3 of p squared minus still log base 3 of q to the fifth. And if I want to simplify, I know that log base 3 of 9 is 2, since 3 squared is 9. And then on the last two, I can just yank the exponents down. So my final answer will be 2 plus log base 2, or sorry, 2 plus 2 times log base 3 of p minus 5 times log base 3 of q. Okay, the next one here, they give us x plus y, or sorry, they give us log of the quantity x plus y to the fourth divided by 7. So the first thing I see is a fraction inside of there. So we'll have log of the quantity x plus y to the fourth minus log of 7. Okay. And now from there, the only other rule I see that I can invoke is that I have an exponent inside of this first logarithm. I can yank it outside. So I'll have 4 times log of x plus y minus log of 7. Notice there was no rule that told us anything that we could do about log of a sum, because we do not have any such rule. So we'll have to leave this one like this. Okay, and the last example here for this part is that natural log of, oh gosh, the cube root of xy squared, then divided by t cubed. So in the first thing I see is the fraction. So I'll break up the logarithm into the sum, or sorry, the difference of two different logarithms. We have natural log of the cube root of xy squared minus the natural log of t cubed. And now I know this might be something from our distant past, but the cube root can be written as an exponent, as the exponent 1 over 3. So in the next step, I'm just going to rewrite this cube root of xy squared as the quantity xy squared raised to the 1/3 power. So I'll have natural log of xy squared to the 1/3 power minus 3 times natural log of t, where here I've invoked rule 7 and yanked out the 3. And now I can yank out this 1/3 here. So in the next step, I'll have 1/3 times the natural log of xy squared minus 3 times natural log of t. And then in the next step, I can notice that I have a product inside of this logarithm here. So I'll have 1/3 times natural log of x plus natural log of y squared. So that 1/3 multiplies both of those guys, minus outside 3 times the natural log of t. And then I'm running it kind of out of room on the paper here, but in the next step, we can yank out the 2 from natural log of y squared. We can yank the 2 out front and then multiply through by 1/3. And so we'll end with 1/3 natural log of x plus 2/3 natural log of y minus 3 times natural log of t. Okay, and so join us in the next video, and we'll see some more with this nonsense with maybe some more concrete examples. We'll see you then.